So welcome everyone. Today we're very happy to have Josh Speagle with us. So Josh received his bachelor's in astronomy or astrophysics and physics. Astrophysics and physics from Harvard in 2015. He then went to the Capitol Institute for the Physics and Mathematics of the Universe in Japan for a year before returning to Harvard to do his PhD or master's and PhD in astronomy, which he received in 2020. He then went to the University of Toronto as a Banting and Dunlap postdoctoral fellow before becoming a professor there in the Department of Statistical Sciences and Astrophysics and Astronomy. Yes. So Josh is an expert in many things, in particular for this talk in astrostatistics and kind of understanding galaxy formation and evolution and structure. And so today he'll be telling us what we can learn from panchromatic images.
Awesome. Well, thanks so much for the wonderful introduction. That's a long list of ways to say that, somehow I've managed to convince enough people that, letting me fit a bunch of models to things and just kind of just generally loving error bars is enough to keep me going. So, so hi everyone, I'm Josh. I'm currently a new, as of July, assistant professor joint between statistical sciences and astronomy and astrophysics, which means that I can officially say that I really love the fit stuff. And today I'm really excited to be at the IES. Never been here before. So I was super jazzed to get an invitation to come speak, to talk a little bit about some, astrophysics oriented work on trying to, use different methods to analyze images, fancy way of saying as spectral energy distributions for stars, to estimate stellar properties and what we can do with them, particularly to understand the Milky Way better, but also just in general. So I'm going to start out by sort of saying a lot of the motivation for why I got into this problem, which is that, when we look out the night sky, I think this is a nice image of the Milky Way. They're just stars everywhere, right? They're just, you see tons of them. They have lots of structure. And unfortunately, they all don't come with like little labels attached that say, hi, I'm here at this distance in this position in phase space. Okay, thanks, bye. Which would be great if we wanted to do astrophysics and really come up with ways of doing galactic structure and dynamics. But unfortunately, we don't. This is one of the most recent versions of this picture, which contains sort of the most pristine data we have on this to date from Gaia, showing sort of the all sky view. I love this just because it shows, in this particular image, Gaia has now detected over 1 billion sources. And so that data volume is just increasing and counting. And the reason this is important is that if we want to understand our own galaxy, right, we're trying to go from this image on the sky and figure out what's like the overall 3D structure, dynamics, assembly history, and other things. And it's really hard to just look at a picture and say, oh yeah, I know exactly how our galaxy formed and how it behaves. And I expect that, I also can say that, but really the one who probably can say that the most is Scott. So the question that I have is really, when you look at other galaxies, which is a lot of what I've done in the past, they can offer insights into what we expect our own galaxy looks like, since we can kind of look at them from afar and zoom out. And so, just looking at it, we can get, some assumptions or approximations about what type of spiral structure there might be, star formation histories, bar dynamics, dust content, basic evolution, a lot of things over cosmic time. And we can use those to stitch together a picture, in particular, the one on the right of the Milky Way, based on lots of these pictures on the left and based on other data we have. But again, this is something that we don't necessarily know ahead of time. This is really artist conception. And so a lot of what I'm really interested in and what I'll talk about today is how we can use stars and all the process of trying to go through a lot of statistical machinery and lots of large data sets to really turn, to use our position in the Milky Way and turn lots of these data into this. So what essentially I mean is that we have this model we want to build in 3D. We have ourselves here. We're going to look at some patch of sky, and that's going to give us this 2D projection and other sort of intermediate quantities we can get by looking at the sky over time. And then what I'm very interested in is going in reverse, right? How can we use these data sets to do inference? So this talk's going to have kind of 5 parts. And the idea is that, each of them will roughly take, somewhere around like 10 minutes-ish. Maybe a little more, a little less if people have questions or comments or just want to chat. I heard this is very informal, so I'm very happy to be interrupted at any point. In the first part, we'll talk a little bit about some fun history background, outlining some of the assumptions that go into it and kind of piloting the problem. In part two will be all the statistics, how we go from data to infer stellar properties and build up a model. Part three is sort of like the first application of this, which is using lots of stars to derive galactic structure, particularly through star-forming regions and 3D dust mapping. Part four is going to be primarily some fun with data visualization, trying to really expand the approach to look at, in particular, Gaia DR3, to look at mapping the galaxy at large and at scale. And then part five, I'll talk a little bit about things we're thinking about with DR3 and sort of going forward into an era of how to incorporate things like machine learning and other sort of inference approaches into this whole framework. So let's start first with history and background, which is that we've been trying to map the Milky Way for a long time. And I know that as someone who's still under 30, long sometimes seems like 2000. But this has been true since the late 1700s. And William Herschel published this really cool plot on the construction of the heavens back in 1785, showing sort of his view of the Milky Way. And of course, the sun's at the center, so we can kind of see that here. But what I love about this picture is how he derived it and how many things about this picture actually he gets right. Which is the fact that the Milky Way has this very pancake-type shape. You have more stars in one direction than others, sort of in the radial direction. You also see a lot of asymmetries where there are more stars on one side than the other, which is also true. There's more stars toward the galactic center than toward the outskirts. And so this picture, even though in many ways, reflects the time, actually has a lot of these key nuggets of information. And I want to go through how all these things map onto the data he was working with and the assumptions that he was doing. So how did Herschel do it? And what does that mean for us trying to, understand how we go from, data on stars today to actually like doing, building up these models? So the idea is that you have some data, of the sky. Herschel is doing most of this by eye. And you zoom in on a particular patch and you see a bunch of stars. And so you can look at this and you can make two assumptions. The first is you can say, I don't know much about what these stars are doing. I see that they have different brightnesses. So I'm just going to assume that all stars are kind of doing the same thing. They all have the same intrinsic brightness. And then of course that means that, using simple inverse square law, that the brightness, the relative apparent brightness of stars is some measure of their distance. So if you can benchmark, kind of roughly speaking, how far away a particular star is, then you can use that information to then sort of calibrate all the other stars, other distances, making the assumption that they all have the same intrinsic brightness. The second is that there's no material between us and other stars. And what this really means is that the number density that we observe is the actual true intrinsic number density of stars on the night sky. So that's sort of outlined here. And that's, if you look at, for example, this picture, that means that when you see more stars in sort of certain quadrants and less stars in others, that's just because there are physically more stars there, not because something is possibly blocking our view of those stars and we just can't see them at all. Now, both of these start to be wrong. And I want to outline, why that's the case in like a very simple review, but also how that makes this inference problem harder. So first, the intrinsic brightness part. When we look at trying to measure distances to stars and determine the intrinsic brightness, one beautiful version of looking at this is just the HR diagram. So we can look on the right, we have this wonderful, Gaia HR diagram with, absolute magnitude on the y-axis and then color on the x-axis. This is labeled, and the colors here indicate relative density of sources. And the thing you'll notice is that, these stars are all shifted to be at the same distance because they have the same absolute magnitude, but they're not the same, right? The brightnesses all vary, and in fact, they correlate as a function of color. And so what that means is that if we have an apparent magnitude, in theory, we can just draw a line, but rather than that line only going through a single point, because all stars have the exact same intrinsic brightness and possibly intrinsic color, we instead get a distribution. And so in theory, we can go backwards and say, great, we observe a star at some apparent magnitude. Therefore, if we match it based on color, we look at the density of stars empirically or theoretically that we expect to be at that color, and that gives us, an estimate of its distance, and that marginalizing over other properties. So that seems straightforward enough. So if this were true, then I think our life would be very easy. And we could just go out, try and get really good data with Gaia, calibrate some parallaxes, and then say, great, let's just go out and measure a bunch of distances by conditioning out colors. The second problem is worse. There's no material problem. As I'm sure many of you know, being at Princeton, which has done lots of stuff with the CMB and great stuff with dust maps, the IES has contributed to lots of material as well. Dust in the interstellar medium exists, and it's pretty cool. But most importantly, dust, while only a tiny fraction of the ISM by mass, scatters up to 30% of all light. And that's a classic reference by Brutus. And so, the picture here is just showing on the bottom, essentially, data from Planck. We have, galactic latitude and longitude here. The color scale is based on the relative color excess, which is a measure of reddening or extinction for dust here. And you can just see that there's lots of structure for dust. You see a ton of it in the plane. And this just means that we're not seeing a lot of stars because dust is blocking off the light.
This number 30% must depend on the line of sight, right? So this is from our vantage point.
It's sort of an integrated quantity over most of the galaxy. So
Like if I look at it face on, I mean.
yeah. No, it's
lower.
yes. No, if you're looking at a galaxy face on versus edge on, you're going to see something very different. So it depends on our relative position. So this is kind of an average one based on where we are. Yeah, but no, it definitely depends on your line of sight. I mean, we're looking at external galaxies. This matters quite a bit, the exact orientation in terms of the amount of impact dust has in the observations. So the primary effects that dust has is just extinction and reddening, which are due to the fact that when you have light that's blocked by these dust grains, that particular scattering process is wavelength dependent. So shorter wavelengths scatter more effectively. So they get attenuated or extinguished. So you can sort of see that here, these two effects. So one is just general extinction. So if you look at, say, the edges of this particular cloud versus the center, you just don't see any stars there because all the light's blocked. And you do see it in the infrared. So that's sort of the first one. The second is that because this scattering is wavelength dependent, as you get more and more dust, you actually, redden the star. You scatter, relatively more blue light than red light. And so that makes the star appear intrinsically redder. And you can actually see that in the infrared very clearly as you sort of go from the edge of this dust cloud towards the center. Stars get apparently redder, even though there's no intrinsic reason to believe that all the stars in that region just happen to have different colors. So we combine all this together. One other thing, which is that dust is also very complicated and doesn't just necessarily have a very well-behaved universal, extinction process. So this is one way to look at it, which is called an extinction curve or reddening law. It's plotted in these weird units, but the x-axis essentially is in one of our wavelengths. So bluer light is to the right, shorter wavelengths, redder is to the left, and this is all normalized, so more extinction is higher. And what you can see here essentially are a bunch of extinction curves. These are derived by David Fitzpatrick about 20 years ago, but still are often used today. And these just show different essentially behaviors based on the size and composition of dust grains. And these do vary throughout the galaxy. So when you look from place to place, the particular way that dust actually both extinguishes and reddens your source changes. People often assume that it's probably something very simple, but it turns out that a lot of studies have shown that this can be quite complicated.
So why the slope in the optical band the same for different power?
Oh, that's so they've been normalized there.
Yeah, but normalization can only guarantee you have the same value at the point, right? But
yes,
not guarantee the slope of the.
Yeah, so this is sort of in like the far optical, where in general lots of these behaviors are pretty similar, and that's just mostly due to how these curves have been defined. So if you sort of move normalization to other points, you'd see agreement around, like, say, the pump or other parts of the curves. In general, you see a lot more variation in the ultraviolet compared to the optical, and then the infrared is really just this long-term extrapolation with this gray component, which determines the 0 point. Yeah, but definitely, if you have questions about this, Bruce Green has a whole textbook on this, and as far as I'm aware, I've never actually met him in person, but I would love to talk about dust.
Can you remind me what is this feature you do?
Oh, this one?
Yeah.
Yeah, so I believe this is the 2175 angstrom bump. And this, I believe people think, they don't quite know what causes it, but I think it's caused by graphites. So essentially it shows up in some galaxies, generally regions of higher extinction. They're not quite sure what causes it, but they think it's essentially some certain composition of grains. Yep. So this is just showing, what this looks like in general.
Is not for, that's not there for the SMC kind of thing, right? The low metallicity galaxies like SMC don't.
That's right. Yeah, that's right. So the SMC does not have those features, and you also don't see it as much in some star-forming galaxies. But there's a lot of variability, and so when you're looking at external galaxies, the strength and presence of that feature actually varies quite a bit. Yeah. This just shows that not only does it vary sort of by galaxy, it also varies a lot in our own galaxy. These are just essentially extinction curves derived from Hubble's sort of high precision photometry and spectroscopy for a bunch of stars in different sight lines. And this is just showing the estimated curve, again, with the same normalization at the same wavelength. So you can see based on it, if you normalize it to the infrared versus the optical, there's just a lot of differences. So take everything that I'm about to say with a slight grain of salt. And this is actually something that we've tried to account for, at least for the first time, as well as we're aware when trying to model stellar properties. So the impact of dust essentially means that this simple thing that I outlined earlier now has this little wrinkle. So before we have a star where we fix its color and then we can estimate its distance directly by just looking at the density of stars with that same intrinsic color. But because of dust, we actually don't know the intrinsic color. It sort of moves along this particular axis. That axis can shift depending on what the properties of dust are. And that means that, broadly speaking, now this entire purple region is fair game. Another way of saying that is that if we have a star that's faint and that it's red, we can consider two possibilities. One is that it actually is just faint and red. So we have a low mass star, it's close by, so it's not very bright. Or we actually have a very high mass star that's quite far away, but instead is blocked by a lot of dust. And that's what makes it appear faint and red, even though it's intrinsically far away and blue. In addition, we have this extra degeneracy. So you'll notice that sometimes we have these solutions where we actually hit the giant branch as well, where you have stars with the same intrinsic color or the same surface temperature, effective temperature, but very, very different intrinsic luminosities because they have very different sizes. And a priori, we don't quite know the difference between these unless we have additional constraints on the age from other sources, or constraints on the distance, say estimated through things like parallax. And that will become more relevant later in the talk when I talk about how we can incorporate, for example, lots of information from Gaia to help distinguish these two solutions. The result of all this is you get something kind of ugly. So here's just a snapshot, essentially a multi-panel figure. Each one is showing essentially the estimated probability distributions for different stars. These are all towards Orion. This is showing essentially dust on the y-axis and the distance on the x-axis in units of distance modulus and sort of attenuation, the V-band and magnitudes respectively. And what you can just see here is that there's a lot of variability. And in general, these distributions look pretty gross. You have a lot of these curving degeneracies. You often have multimodal solutions because stars can be on opposite sides of the galaxy. Stars can be a dwarf or a giant at different evolutionary stages or have different metallicity solutions. So it's just not great in general. And so finding a way to come up with these probabilistic estimates is going to then be sort of the next part of this talk. But as you can see, inference struggles here with large uncertainties, complex degeneracies, and multimodal distributions.
So each panel here is like a pencil beam in a particular direction.
Yes, yeah, it's the line of sight towards a particular star. Yes, but all in the same sort of general area towards Orion.
What is the unit here? Distance in what?
It's in log units, so it's in distance modulus. Which is in magnitudes, but fundamentally in log parsec. Yeah. So at least the pitch that I'm making is that widespread application, if we want to use stars to do galactic structure and galactic dynamics, we need to solve this problem. So we're going to need large sample sizes to deal with these large and complicated uncertainties. We're going to need more, better inference approaches. and then also significant computing power. I'll sort of go through what we can do to try and resolve these things. One thing I want to address for people who might have some background in this is that there is an alternative, and this is what a lot of the community has used prior to stars, because they looked at this and they said, okay, stars are hard. We should use something that's much better. We can get very good distance estimates to them. Masers are great because you go to star-forming regions, and because these are all emitting in the radio, you can get interferometric parallaxes to them using like very long baseline interferometry. The AHT group obviously does great work with all this type of stuff. So there's radio expertise here. So that's the idea. And also because in the radio, we don't have to worry so much about dust. So masers, excellent. The con, of course, is this is very time consuming. So you need hours of observing time per source. And generally, there have been several observational campaigns, one of which I'll show in a second, that have done this for thousands of hours only for like 100 sources. Now, these are great. And in fact, what I'm going to do is I'm going to show this sort of picture here. The one I showed in the beginning, if you look at the background, that's the artist's conception. The overlay is actually a very faint, transparent image of the actual data colored by various spiral arm fits that you can see very faintly. And this is actually the 100 masers or so that are used to inspire this figure, that were used to create this artist's conception and derive structure. So this is the approach that was taken before. Over the past few decades, has been getting, spending a lot of observation time to get this very, very small but very high quality data set. And it's been very good in figuring out a lot of things. But now that we have these big surveys online, we have billions of objects and counting. The question is, what can we do now that we have those large numbers? So that's the reason that we want to scale up. So masers are rare, they're very time consuming. Stars are common. Images are super cheap, for instance, involved with things like Hyper's Prime Cam, but also surveys like PFS. And in general, we can get just much more data from doing imaging. And now we have a lot more compute power, and computing has become much cheaper in general to run. And so often it's much cheaper to actually, run your telescope for some time to get an image, and then spend a lot more computing time processing that image than going and trying to do very expensive follow-up spectroscopy or other, other observations to get really high signal to noise data. So with that in mind, the question now is, how are we going to infer stellar properties to these things? Like, what's the, what's the actual approach that we're going to use to solve this problem? So we have a couple of requirements looking back at sort of this particular figure. We need an approach that can do two things. First is that it can characterize these sort of multimodal complex parameter degeneracies, and you can do it robustly. We don't want to miss solutions. But if we do that systematically, we're going to get galactic structure wrong. We're going to put stars at the wrong distance, and we're going to get results that are nonsensical. So we need to make sure we can do that right. The second is that it needs to be fast. If we're running this over hundreds of millions of sources, and we want to make good use of our compute time, our hope is that we can get a method that runs in seconds, not one that runs in minutes. If we really want to scale up and not have to take over an entire cluster, to run like a cosmological simulation level of compute hours. So our approach is that we want to use a Bayesian modeling approach to simultaneously estimate two types of parameters. The first is what I'll call intrinsic parameters. These are things like the intrinsic brightness or the stellar type. And then we have extrinsic parameters. And these are things like distance and dust, things where the star is the same, the only thing that's changed is where it's located in the stuff that's between it. And so we can write down a model that looks like this. And this is just an application of Bayes' theorem, where we have on the left essentially is the probability of these intrinsic parameters theta and these extrinsic parameters phi, conditioned on our two observables, which I'm going to say are the observed magnitudes and the observed parallaxes. So we have our observed brightnesses from images at different wavelengths. We have our measured parallaxes. So this is where our nice panchromatic title comes from. And then we have what I call the galactic model prior, which is our sort of prior belief about what the galaxy kind of looks like and is made of. And we want to make sure as we test this, how sensitive we are to that sort of particular assumption. So the images are actually quite straightforward, but they involve this interesting combination of nonlinear and linear dependencies. So this is kind of writing things in a more statistics-oriented approach. So the idea is that we have some measurement error that we assume is normally distributed with some covariance if we, say, have covariance between the images based on how they've been processed, for instance. then we're saying that the observed magnitude is equal to the intrinsic one based on the stellar type or these other parameters. And then there's going to be some set of linear coefficients that multiplies the extrinsic parameters. So that's the distance and the dust. So one of them is just going to scale the star, the overall brightness. And the other one's going to affect it in some particular vector that will change its color. And then we're going to add some observational uncertainty. So that's the basic model. So straightforward, it has this nice break between sort of a linear part and then a nonlinear part. Our parallaxes are even simpler. Gaia has gone through a lot of really, really excellent work, in all the data release papers from DR2 to EDR3 to really show that they do an excellent job of error estimation. And so it's a very, very good accuracy. We can assume the errors are normally distributed, which is great. In this case, then the only fun part is that the actual distance is inversely related to the parallax. So we have to do some parameter transformation there. Finally, when it comes to our galactic model, we assume a pretty standard approach. We're mostly going to, in this talk, avoid sort of the central region of the galaxy. So we're going to not really worry about the bar or the bulge. So we mostly just assume the galaxy has roughly a thin disk, a thick disk, and a halo, which have different age metallicity relations and distributions, and then also some number densities that are estimated from, in particular, a big review by Gerhard and Bland Hawthorne, and then also from SDSS. So that's our basic assumption. We don't do anything too crazy. We try as much as possible to pull from the literature for this. We do test that some of the predictions don't change too much if we shift some of the priors around a little bit. Once we have that, the question is, what are we going to do about getting our results? So we've written down a model. Now we have to figure out how to actually use it and do inference. So the problem here is you might imagine that typical approaches, in particular ones like for those who are familiar, Markov chain Monte Carlo approaches, really struggle with this problem. It's not easy. You have multiple solutions, so we need something else. So, in this approach where you're just kind of randomly walking around, you're going to miss solutions, and that's not going to be feasible. So one alternative is nested sampling. This is a nested sampling talk, but this is definitely, an area that I've done a lot of work in. And, a few years ago, I published this nice package called Dynasty, which is, now been used more widely in literature to do inference that takes advantage of a different approach to doing sampling. And in a very broad overview, nested sampling essentially samples in these nested shells of these isolikelic contours. And so what you can see here is that you start from the edge, you kind of sample inwards. And when you identify structure, you can actually fragment and sort of sample them all separately at the same time. And so that allows you to sample very cool distributions like the logo, which I enjoy using as sort of a self-explainer on how nested sampling works. I'm happy to answer more questions afterwards on exactly that, or if people have Dynasty questions, hopefully the packages work well for you, and if not, I'm very sorry. So our second solution was Dynasty is great, but it's too slow for our problem. It's actually a very generic solution, and we need something that's more bespoke or artisanal, just like people often get with their coffee. And so we want to really throw the kitchen sink at this. And our solution was really essentially looking at the statistical properties of all the different parts of our model and seeing where we could simplify. The first, insight that we had was that for a given stellar type, which is these intrinsic parameters, if we condition on them, we actually have a Bayesian linear regression problem. We're trying to solve for a set of coefficients that have a linear dependence with some known vector, and we have some priors on them. And so that means that what we can do is we can essentially use a lot of pre-existing math and analytically solve for phi, which is for the distance in the dust conditioned on a particular stellar model. And that essentially happens more or less instantaneously. We can also get uncertainties out and include lots of priors if we keep them in certain particular functional forms. So that allows us to solve at least some portion of the problem immediately. The second part is that because our intrinsic stellar models actually are quite low dimensional in terms of how they behave, they really depend only on mass, initial mass, metallicity, and age, more or less. That means that we can actually explore them really efficiently by taking advantage of vectorization, other computational methods, using a very brute force approach, which seems super simple to just grid up the parameter space, but actually works really well because you can just parallelize this, you run it, and it goes really, really fast. So this means that we have sort of two solutions here. So we can solve kind of the problem of fitting a stellar template to a model by essentially treating it as a linear regression problem and then just parallelizing it like a million times. And that happens for every single star, like in just a few seconds. The last stage is then incorporating these other parts of the model, in particular constraints from parallaxes and constraints from our prior, which are not as well behaved. And in that case, our assumption is that our initial fit is probably going to be a reasonable guess. And so what we can do is we can use a method called inference sampling to essentially resample a bunch of possible solutions from our best estimate and then reweight them based on what our prior is doing. And so that looks kind of like this, where we're assuming that we're sampling from kind of this distribution Q, which is green, and then our actual true answer is going to be something like this in purple. And so by taking a bunch of samples from Q, we can reweight them to get them to look more like the purple curve. And that also happens only over a few seconds. And so the final takeaway is that we do all of this and we get out what's shown here on the right, minus the floating text bar, which is essentially what you see. It works very well. And this all runs in just a few seconds for most objects. It runs even faster if you have very strong constraints and you don't have to do as much additional work. It runs a lot slower if your actual data are pretty much uninformative and you have to really test out every possible model. So the code also is public. One thing I care a lot about, as you might have guessed from the previous package, is making public, hopefully easy to use code. So the package is called Brutus, and it's Python based and open source, and you can access it on GitHub. I do not have documentation up for it right now, but I do have a lot of notebooks that go through some of the basic functionality. Hopefully, we're going to get the paper resubmitted in the coming weeks and post to the archive along with some nice documentation written up. If you're interested in using it, feel free to take a look at some of the notebooks that are included. It has a bunch of fun utilities that I've added to try and do this. And it doesn't just do this sort of thing. You can also use it to query a particular set of stellar models and also query isochrones. So for people who use stellar models in general, I have some nice interfaces to help out with that. So the third part of this is now I've gone through all of this background, all of the statistics. Now let's go to the application, which will involve sort of building off of this baseline approach in these data products and to build more statistical models to see what we can learn about galactic structure. And the first part is going to focus a little bit more local on the solar neighborhood, because that's sort of where some of our serendipitous discoveries first came to light. So I showed before this sort of artist conception of what the Milky Way looks like. And and in general, the way that we have fit for and identify spiral arms is that these are locations where new stars are preferentially born and have sort of common rotational velocities and common kinematics. And we should see that, for example, when we look at data on gas or dust in like the radio. And so mapping out these star-forming regions is a really effective way to trace spiral structures. And those tracers include, young stars, gas, and dust. And that's why when we look at sort of the artist conception of the Milky Way, people use masers for this, because masers preferentially trace star-forming regions, therefore they trace out spiral structure. And if we then compare those to data from lots of gas observations from H1, from CO, then you can sort of piece together some basic model for what we think the Milky Way spiral arms are. This is by no means a solved problem. Just as recently as like 5 or 10 years ago, people have been debating the existence of other stellar arms or sort of armlets or connections between arms. So this is still very much an open area of research and debate. Now, what I described earlier is this problem where we have a bunch of dust, and that makes individual stellar observations more uncertain. Now, however, what we can do is we can actually turn that particular weakness into a strength by leveraging the fact that we have a bunch of stars, all of which are reddened and extinguished in a slightly different way. We can actually use that to build up essentially the distance and distribution of foreground dust from many stars. So we can pool this weak information together over hundreds, thousands, tens of thousands and millions of stars to construct essentially a 3D dust map. And this then gives us some insight combined with, say, gas measurements to actually get at both distances and properties of star-forming regions, but also broader scale spiral structure. And so I want to outline exactly the very basic approach that we took, because this is what I would consider like the simplest model that we can construct. So this work was done with Catherine, who was at Harvard. Now she's actually at Space Telescope. The basic idea is if you look at a particular cloud. This is data from Perseus. And we want to know, like, what's the distance to this broad structure? What we can do is we can lay down a little pencil beam in that direction. And when we, along the pencil beam, we have some model for what's going on. So I've just sort of zoomed in this pencil beam up here. This is now looking at the projection along the pencil beam as a function of distance modulus, and again as a function of sort of log dust or extinction in magnitudes. So our basic model has like 3 parts. The first is that we have some basic foreground amount of dust that's very close by, that's a little hard to probe. So there's some, background offset that we have. Then we have a bunch of stars in the foreground. So they're going to be in front of the cloud. They're going to have a tiny bit of dust. They're going to have some small scatter. Then we're just going to have the cloud is like some delta function. That just all the gas is going to be in some very, very thin blob that's relative to the overall distance of that gas cloud. So it's a step function. And that's going to be the amount of dust and the distance to that particular cloud. And then we're going to have a bunch of stars behind the cloud. And of course, every star is not just a single observation. It's a real probability distribution, which is highlighted here, sort of as a shaded region. And so we need to marginalize over all the uncertainties on individual stars in order to make this measurement realistic. We also imagine that there's some intrinsic scatter, because inside this pencil beam, there's some intrinsic variation of dust that we're not capturing, since it encompasses some finite area. And finally, our models are not perfect, so we're going to get some of the answers wrong. Misidentifying giants as dwarfs will sort of put stars way up here when they really should be way, way, way over here, and vice versa in this place. So there's going to be some cases where we just mismodel them completely, and we hope that those don't, are a minority of cases, but we'd like to include a model for them.
Don't you have like parallax measurements for this?
Not all of them. And I'll actually go through, we have a lot in the foreground. So in general, we have a ton of parallax measurements here, and then we have some weak parallax measurements here and very little parallax measurements out here. And so that actually determines a lot. I think actually it's one of the next slides that is going to be how parallax affects this inference. Yeah, so you're one slide ahead of me. So the parallax measurements with Gaia have been a key factor in enabling our results, in particular for this exact reason. So if we look at before Gaia, this is essentially running over the same data with our models, but ignoring all the parallaxes. This was done in Eddie Schlafly's work in 2014. You get sort of these results shown here on the right. Now, when you add the parallax in, you get some very interesting changes. So I'm just going to flicker between these two so you can sort of see what happens once we add in a parallax measurement. So you'll notice that there are a couple different things that happen. First, I'm going to zoom in on the one on the top right. So you'll notice here we have, this is a foreground star, and we have a very, very precise distance measurement from parallax. And so if you just look at that, I can even zoom in like this, you can see that what happens there is essentially the error bars just shrink to be very, very small. So that's great. For a lot of other stars, especially ones that are further away, what you instead see is different behavior. We have these 2 solutions, for example, and often what happens when you add a parallax is it will pick one of them. So it will disfavor either a close solution or a far solution, depending on the measurement for the parallax. In general, even if parallaxes are very low single to noise, but are close to 0, those can often rule out close distances, which is what you actually see. And for example, trying to see which one, like 9, for example, in object 9, you actually see it picks the far distance instead of a close distance. But it doesn't actually give any extra constraints on the distance. It just disfavors, half of the solution. Because the parallax constraint is weak. And so you see like there's lots of cool behavior, and in some cases we get really strong constraints, in some cases it just shifts the distribution around, and in some cases, like say in 10, it doesn't even do anything. Like the parallax is so weak that it doesn't really change our inference at all. So this has been great for us and allows us to really get much better distance measurements. But what I should say is that it allows our distance measurements to be dominated not by statistical uncertainty, but by systematics, which is the fact that we know our model is way, way too simple to really model clouds correctly. It turns out that this can sometimes also be fun, because if you have, for example, an object that looks like this, you'll notice that in this picture, we're just showing all the individual stellar posteriors. We've used crosses to better indicate kind of the centers of these. And what you'll see is that there's actually a bimodal distance solution to this particular cloud. This is chameleon, where that's shown on the top. These sort of histograms show the overall distance solution, because it's unclear whether to put the cloud here, right after these 2 stars, or right here, which are essentially right, when this whole wall of stars appears. So there's an interesting case where if you don't have a lot of foreground stars, in this case, we only have like 6, it's very difficult to actually place exactly the distance to that particular object. So this means that we actually get to go back to what I described earlier, when I said that maybe we could use, for example, dynasty, and I chucked it out because it was too slow. Now we can add it back in, and we can sort of solve these types of interesting questions. Now I think it's some of the fun part. So how well do we do? I sort of outlined that, stars are cool. We love them. We want to use them all the time. And so one reason why we want to use stars, they're just accessible to many, many more sources. And what we did was we actually compared the distance measurements that we get from our method, which we call dust distances based on all of these individual stars, to estimates we get from masers. And in general, we get not only excellent agreement along the one-to-one line, we do actually out to quite large distances, over 2 kiloparsec. Beyond that, systematics start to come in. So we really don't trust our distances out there better to like 10%. But this is great and implies that we should have confidence in this method when looking at some of the subsequent results.
So these are distances to the clouds.
Distances to clouds, yes. Assuming that the maser is sort of embedded inside the cloud, and so it's a good tracer for that particular distance.
Right, okay. So you need some stars that you can see behind this cloud.
You do need stars that you can see behind the cloud. Yes, that is a limitation of this method, is that we need to be able to see through the cloud, and also that in general you can, that often leads you to be biased towards the edges of the clouds where there's less dust. So in general, the method that uses all these stars generally is more sensitive at sort of the outskirts of the clouds, whereas masers tend to be deeply embedded and so generally are much more sensitive inside. So it's not quite exactly the same region, but in general, as the clouds are pretty concentrated, they end up tracing a very similar distance.
And this double solution, I mean, that will how much would show on this plot?
Oh yeah, we just inflate the error bar. So in our case, like for this one, our error bar would be, quite large. In this case, you see it's 148 minus 3, but plus 39. So we actually have quite a large upper limit because we're not sure how far
So
we
you have a maser?
This one does not. No, Chameleon has no maser. Yeah. So masers are only available for a handful of clouds. I think these are all of them, actually. So we have distances to a much larger set of objects.
Some giant stars also have masers, right? Like envelopes of stars.
Yeah, so there are other masers that exist, but generally for this particular comparison, we need ones that are associated with these star regions. So these are all the main ones, at least from like the vessel program that, and I think goblins that we use. Yeah. So I want to highlight a little bit like what this actually looks like in practice. I want to use a particular called Cepheus, which will bring me to the first fun interactive figure for the talk. So when we publish these paper, I love actually doing like fun interactive demos to show what stuff looks like. And so here's one where if you actually click on various like parts of this figure, the color actually shows the distance modulus. These are all the clouds that are labeled. And so, for example, if you click on Cepheus, it will pull up an interactive figure of Cepheus. I've also done this ahead of time in case the loading is slow. You go over on the left, it'll sort of show you, broadly speaking, what the Planck, integrated extinction map looks like in the position. And if you go on the right, you get the fun part, which actually shows you the fit in every single pixel. Along with sort of the general solution, you can see all the best fit parameters and every star that's gone to that fit. And what I love about Cepheus is you can see very clearly that this cloud is actually 2 clouds, sort of Cepheus upper and Cepheus lower, one of which is located very close to the foreground. The other one, which you can see here, is located in the background. But this also shows where our model starts to break, because this foreground cloud, which you can see, occurs earlier here, is instead swamped by this background cloud. We definitely do not properly encompass the fact that this background structure seems to be quite extended. So we're just fitting like kind of a middle distance for this, since our model is so simplistic. And you can see as you move kind of, what parts of that foreground structure kind of go away and start to sort of fade into this background structure. And you can see here, for example, places where the fit is a little uncertain because you don't have a lot of foreground stars and it sort of switches around. So this is available for every single cloud that we publish because we don't want you to just like take our results as gospel. We want you to actually look at all of them, see all the data, look at the fits, and judge for yourself and be able to make connections. Yes.
So you may have already said this, but do you let different fits from different things talk to each other, like do ensemble?
Not here, but that is one of the things that we're working on now. So I don't talk about this here, but I have a student who's working on doing exactly that. sort of doing not just a pixel by pixel modeling, but a full actual 3D density modeling approach to do this, which would talk to each other.
Or you have some correlation structures.
Exactly. So putting correlation structure in general, having a functional form that's smooth, so it cannot vary arbitrarily from pixel to pixel, sort of implicitly. Yeah. So they're using deep learning to do that. Using some fun approaches to incorporate uncertainties and outliers and things like this. But I don't have that at the top.
Here, you just assume there's one cloud in the left side.
That's why here, for example, you can see we don't do a good job. We do have a version that includes multiple clouds, but for consistency, we did not include that model in the.
Yeah, just also ask, will it improve a lot by just adding another?
Yes. So it does, and if you're interested in that one, we have a paper with a now graduate student at Caltech, Kaustav Das, on driving the distance of the North Polar Spur, where we actually do allow our multi-cloud fit, where we fit a bunch of possible foreground structures, and that becomes important there because there are multiple foreground structures. But for this one, we chose for consistency to just assume that every pixel has the same models. We didn't have to go and sort of do some ad hoc comparison of which one will have one cloud or two clouds or five clouds, just for the interest of simplicity and consistency.
We have like some line measurements, like some carbon monoxide.
So for this one, we're just using stars. There is a separate paper that Catherine led where she also uses data from one of these gas cubes, in particular CO, and uses the velocity kinematic structure and associates them with particular components, and then uses that to actually fit a joint model for all of those. So if you're interested in looking at that, she has a wonderful plot in that paper which shows these correlation structures among distances and kinematics from CO, specifically for Perseus.
Adds to the like.
It does add to the constraints, yeah. So it does add to the constraining power for some of these. We did not replicate that analysis for all the clouds because it was very intensive, and in general the solutions are we think there's a better way to do it than what we did there. That was kind of a very brute force approach. But hopefully this is cool, and as you can see, we have a lot of clouds that we fit for, and some of them are simpler than others and at a wide range of distances, and so you can go through and sort of see where we do well, where we don't, and often in cases that we don't, we mentioned it explicitly in the release paper. So that's like one of the cool figures. But I think that's all meant to give you some confidence when we show you this plot, which is essentially the nearby galactic structure that we're looking at. So the background grayscale is the 3D dust map by Greg Green. So this is kind of the Baystar 19, Baystar 19 dust map with Gaia DR3. And then all the little circles are derived using our method. In particular, what we noticed as soon as we actually plotted this data in 3D and sort of this top-down projection, heliocentric projection of the galaxy, was first you see a lot of structure, but the second is you actually see this humongous line that seems to just extend in a very weird way. If you expect that there are systematics in our approach, it should be along the line of sight. It shouldn't be in some weird curve that extends, parallel to what we expect to see. And that actually turned out to be coherent, sort of not only in this, very visual top-down way, but also we sort of looked at it in 3D. And that led to what we call the Radcliffe wave, which connects a lot of these star-forming regions in this sort of 2.5 kiloparsec long filament, which was led by João Alves from the University of Vienna, and led to at least my first Nature paper, which of course means it's probably wrong. But I was very excited about it, and it looks quite nice. We have a bunch of consistency checks we include in the paper, but it's kind of this damp sinusoidal oscillation that, as far as we can tell, has, is not a long-lived feature, or at least doesn't seem to have a lot of old stars that sort of gravitate towards the potential. And this is also cool because in star formation, people talk about the Gould's belt for a long time, which is this ring, essentially, of stars that sort of extend out in this direction. And this particular model kind of very much seems to refute that and says that a lot of those associations really were just projection effects. Once you can see 3D structure and sort of look at things in different ways, then you actually identify this very, very long contiguous thing. So we also estimate something like 60+% of the mass in the local spiral arm is actually contained in the structure, which is pretty cool. And was definitely not what I expected when I was asked to do some statistical modeling for this. So that was fun. Catherine's also done follow-up work on this too, which led to her second Nature paper that I'm on. And so she sort of looked at this inner region, the local bubble here, and tried to do additional 3D modeling of that using the same sort of data set that we have with additional kinematics and parallax and proper motions that come from Gaia and other radial velocities. And then she was able to show this really nice three-dimensional structure for the local bubble, including a possible origin and expansion history, which was really fun. So essentially, these data products have been super useful in deriving local structure, and have definitely, at least for me, kind of revised a lot of what I thought in terms of how local star formation has gone. And so that's just a plug to say astrophysics is cool, and fitting a bunch of stars and using them has been extremely informative, just in a wide variety of things that we didn't expect. So there's a lot of sort of data-driven discovery happening here. Part 4 is really just a way for me to segue into another really fun plot, which is an application that we're looking at. And this is trying to think about how do we take this basic approach and expand it outwards. Stars are great. How can we use even more stars? So we want to map all of them, right? Before I'm talking about these star forming regions that rely on 3D dust mapping. But now, what if we just want to fit everything, right? Just go out, go wild, and see how many stars we can do. So this is what I call Augustus, and was sort of the second component to my PhD. And the idea here was to just get as many objects as we can model feasibly in a few months, and then as a proof of concept to see what we could do. So we grabbed about 170 million objects, and we call this the Augustus catalog as the first thing to come after Brutus. And this was modeling everything that cross-matched between pan-stars and Gaia with two conditions. The first is we cut out the plane because there are way too many stars in the plane, and we were more interested in the halo to start. And the second was we have a magnitude cut of about 20. And that was, again, really just to make sure we had enough density. And at that point, we also start losing like a lot of Gaia. So Gaia is obviously dropping off throughout the whole process. We really wanted to make sure that we were including as much of that parallax information as possible. When doing these fits. So we also included some additional data from the near-infrared, from 2MASS and UKIDS, as well as UNWISE and the further infrared when it was available, which really helped a lot of the results. So we do pretty well, which is we're just taking essentially our basic result, this basic framework I said before. And what I'm showing here on the left and the right is essentially comparing to two different approaches to estimating distances. The one on the left, which is Anders et al. This one uses Star Horse, which is a slightly different approach that relies a little bit more on grids. But you can see we get very, very good agreement with the Anders et al. Results where we have good overlap with Gaia DR2. On the right, we actually use data that we had not looked at, which is essentially the Baylor-Jones distances from Gaia DR3, and we also get excellent agreement with them, out to quite large distances. And so this gives us some confidence that we're doing something right. We have two different independent approaches. All of us end up with very similar distances. And so now we want to see what exactly we can do here. Yes.
What happens around the material process? What the dispersion actually?
What was that? What's happening like here?
Yes. So you see.
Yeah. So what's happening here is this is roughly the point where we're going out to several kiloparsec. And so we have this region where suddenly we're transitioning a lot to giants. And so this particular dispersion here is because for the Anders et al. Results, there is some disagreement sometimes about whether a star is a dwarf or a giant. If it's dwarf solution, it's a lot closer. If it's a giant, it's further away. And so that's what's happening. Is why you get this secondary bump, these places where both of our methods are disagreeing about what type of star it is. We actually get much better agreement with Baylor-Jones, which uses more, upgraded parallax data and more flexible data-driven model. And so that I think gives us the confidence that we probably our solutions are more likely to be correct, but not guaranteed. There are other reasons that we looked at in the paper specifically related to estimates for dust and intrinsic temperatures for stars. But I think overall, all the methods do pretty well. Hopefully that answers your question.
Yes.
Excellent.
We have about 5 minutes left in the hour.
Yes. And so for this, I just want to essentially showcase as we get to the end, some fun stuff, which is just looking at some visualizations. So the idea is essentially that we look at like a shell around our, around the sun, and we project it onto, the same galactic, central coordinate system. We're gonna get something that looks like this. And if you zoom in really closely to this plot, you'll notice there are actually arrows that are sort of everywhere. Those are derived using proper motions from Gaia. So you've added those in and then converted those based on distance to actual, tangential velocities. And I've used those to indicate both directions and amplitudes for all of these plots. And what you can see immediately is you get this nice break between the halo and the disk. If you go much further out, you actually see great evidence of flaring and sort of this far disk. And this shows up really clearly if you actually look at the velocities. So you get these very coherent motions that are moving quite fast in the same direction. And this is really nice confirmation of stuff that people have seen in lots of other places in the literature. So what I think is cool, though, is we wanted to see what we could do with all this data. So we have 170 million stars. We wanted to ask, can we see sort of bulk flows and motions? And so we hacked this wind map or like ocean current map of the Earth. Instead, we took all the continents out and we replaced them with Gaia, with data from Augustus and Gaia. And that gave us what we call all sky. So I'm just going to go back to the base view for a second. So this is kind of what most time you see in a 2D plot in a paper. And you'll notice here this is an interactive plot. So when you go over different regions, it actually tells you different properties of that region. Right now, we're looking at velocity at a particular position in a particular direction. You can move around if you would like to say, look at different versions of this projection. You can see little animations, which help you visualize both flows and directions. You can see, for example, the first hints of other types of structure here. This particular distance slice or large collaborator clusters, which have very large and discrepant, velocities relative to the overall background in the halo. And we can look at other things like, say, stellar density, which confirms that these are indeed clusters that have a bunch of stars in the same, 3D position. We can change distances. So you can look at, say, different distance features, say at closer or further distances. But what I love the most about this plot is that it allows us to actually look at things the way that I think they should always be plotted, which is on the surface of a sphere. And this allows you to see very clearly where we have gaps in the data, say, in the south, because we're using pan-stars. But also you can see like really cool structure, like for example, Sagittarius, which is just cuts through so cleanly in this plot. And you can see just this bulk motion very clearly picks out the structure serendipitously, based on both the overall number of stars in a given region, but also just their overall velocity structure. If you look really closely, we actually also identify Sagittarius and metallicity as being slightly more metal rich than the background in our halo. It's a little hard to see here. There are some plots in the upcoming release paper, which make that a little easier to see. Plus, you can do cool things like if you look at super close distances, you start to see fun effects like all the stars appear to be metal rich and all of them stream in a particular direction, which aligns with the fact that you're looking at things very close by. They're all kind of just passing overhead or passing around you. You really have to go much further out to see all this different halo and disk interface and things like that. So this I think is really fun, and this website is public, by the way. So if you are interested in playing with this or showing this around, please feel free to take a look and offer feedback. We're hoping to make this better, in future iterations. Okay, so before I go on, I had some extra material that I left in the abstract, where if there was time permitting, I would be happy to go through, about another extra 5 to 10 minutes of stuff, sort of looking ahead at Gaia DR3 and future applications. Or if everyone wants to go to lunch, I'm happy to end the talk here and just jump straight to the conclusion. Any votes? Benevolent dictator George?
Maybe quickly go through, because you said there's machine learning.
There is, yes. So that's actually the most direct part. We use that. So the idea here is that, we're really interested in looking at Gaia DR3, and that is amazing because it has BPRP spectra. And these are, essentially moving from a few bands of broadband photometry to actually low resolution, but flux calibrated spectra over most of the optical wavelengths is a huge game changer. Here's like some plots I took from one of the calibration papers, just showing how this low resolution spectrum, which is shown in black, compares to both a resampled version of a high resolution spectrum, which are the sort of light blue points, and then the actual spectrum itself, which is in yellow, I think from SDSS. And it's pretty cool. So the idea is, what can we learn from this, right? I've already shown you that we can do a lot with panchromatic images. What if we now talk about actual full low resolution spectra? You should see a lot of information there. So one reason I want to include this is because this is work that's been done by Jeff, who's in the audience and is now a new grad student at Princeton. So hi, Jeff. And Jeff essentially has been developing a probabilistic machine learning framework to generate predictions. And so what we did was we essentially, when Gaia DR3 came out, Jeff essentially took a very high quality sample of about 50,000 red clump giants, cross-match between apogee and then also Gaia DR3, and using abundance measurements, other age estimates from astroseismology derived with AstroNet, and then try to see what we could do. And here's what we get, which I think is kind of incredible. So these are predictions essentially from these low resolution BPRP spectra, based on the actual measured spectra, trying to predict, for example, things like metallicity, magnesium abundances or alpha abundances, surface gravities, effective temperatures, and ages. What I think is just amazing is that we can actually do, like 0.06 dex scatter from the BPRP spectra alone, which is great. We actually get real constraints on alpha element abundances, which shows up. And that's been really cool. We've confirmed that's not just correlation. There is real information there, even if it's weak. We get excellent constraints on other parameters. In particular, we can get constraints on the ages. So this has been really exciting. And the plots I want to show you essentially is that Jeff has now extended this to a broad selection of about 2.5 million spectra that we have not trained on or tested on to see what we get. And so these two plots are showing entirely predicted quantities on every single axis. So the x-axis is predicted, the y-axis is predicted, and the colors predicted, and the number density is also predicted. So the number density is shown here as these sort of slight contours. And then the background color is all showing the ages, or in this case, the metallicity. And these are showing the sort of iron over magnesium plots where you see this bimodality and also effective temperature versus log G. So these sort of like Kiel diagrams. And what you see here is that first, we actually are able to recover the bimodality, which is something that the Gaia team noted specifically in their release that they were not able to do for using some of their machine learning models for these BPRP spectra. So we both recover them in density. And we also see very strong correlations with age, which is exactly what we expect. And we also recover lots of sensible correlations between metallicities and general location in these Kiel and HR diagrams, which is awesome. So this gives a wonderful consistency check of our model. And even when we do very simple applications, looking at our selection of stars projected as a function of galactocentric radius and also height off of the disk, we see very, very reasonable results in terms of the overall density that we estimate for our stars based on parallaxes, and then corresponding with age gradients, metallicity gradients, and also magnesium gradients, which actually correctly, you might expect, actually trace ages when they trace iron. So all of these at least seem to give good consistency checks. These predictions not only seem robust, but actually quite reliable, and suggest that, for some of our future applications where Jeff started running more larger scale models over a broader range of parameters for the full sample of, more than 100 million stars, that we're going to find some cool stuff. So that's kind of where I'm happy to end. So I'll just skip right to the ending slide here and say that, it's hopefully this was fun in the sense that it contained a nice mix of, various parts of what I think makes stars really cool. We got history, a little history lesson with Herschel, which I always think is such a fun story about how we actually got the first Milky Way map. I talked about statistical modeling and why we need to, what we need to do to actually scale up these problems and how, my collaborators and I have tried to solve them. We found some cool discoveries in the local solar neighborhood using this. I showed you some cool data visualizations about trying to look at the galaxy at large and being able to essentially rediscover lots of features that people have found very serendipitously. And then finally, I didn't show this plot, but essentially the future looks very, very bright in terms of being able to use machine learning methods and understand them and apply them to upcoming data sets where we don't have as good models or theory to really understand how we can get predictions. So hopefully that was fun, and thanks so much. And I'm sorry to keep you slightly longer than noon for lunch. Thanks.
If we have any very burning questions, maybe we can take one. Doctor's also here for the rest of the day, though his schedule's busy for the rest of the day, and then he'll be here tomorrow. We also have a dinner that there are a few spots left for. So if you want to go to that and have not signed up, either sign up by 1 when I make the reservation or tell me beforehand. And if there are no burning questions, then I think we can all go to lunch. So let's thank our speakers.